Hello everyone, as you know, my name is Daniel Fernandez. I'm the owner of scienceinhydroponics.com, and today I'm going to be doing a video explaining a very important concept, which is the concept of moisture retention curves. So this is very important because this is one of the main ways in which we can characterize media and tell whether a given medium is better or worse than another. So let's think about our medium in soil is growing. So we have normally something that has some particle size. And we are going to add water to it. And one of the important things that we care about is how this water interacts with this media. And this is what moisture retention curves are all about. So the first thing that we see that is important is how much water remains after we water this media. So how much of this space that we have here, of this total volume, is gonna get filled with this water. And this water volume is what we call the volumetric water content of the media. And this is normally defined as the volume of water over the volume of media, so the total volume of media that you have. So this means that this value will always range between 0 and 100%. 100% you will only find if you have basically a bucket full of water, and then you will get lower and lower as the media fills more space compared to the water. Now the second property that goes into the moisture retention curves, besides this water content, is something that we call the tension of the media. So this is a very important concept because you have your particles here. Let's think about these particles of media here. And we have all this water surrounding these particles. When the media is completely full of this water, the tension here will normally be 0 because the water is freely available to anything that wants water. Now, what happens as we start to dry the media? So we have the same media, but now we have less water. And the water will start clinging to the media and we'll start getting these air pockets around the water. Now, the amount of water in this case is limited, and the media will try to hold onto this water. So anything that wants to get this water will need to fight the media in order to achieve this. So here we have some pressure that is gonna be greater than 0. Because, well, greater than 0 meaning we always measure this negatively, so it will actually be lower than 0. But this is basically a pressure that is exerted by the media to hold the water. So if you wanna get that water, then you will need to exert pressure against this pressure done by the media. How we measure this is that we have the media here, and we put an instrument in that we call a tensiometer. And what this is, it's basically a vacuum field. So we have a vacuum here, and then we have a membrane here that is normally a ceramic membrane. And we have no air here. And we have basically a ceramic membrane here that can let water through very slowly. And what we'll measure here, we will add water, and as the water dries, this here will increase, this pressure here will increase, and this measurement of pressure here, how much this vacuum drops, will tell us how much force is needed to be done in order to draw water in. And this pressure that we measure here is what we call the tension of the media. This is also called the matrix potential. So if you ever hear the term matrix potential, it's related to this. It will always range between 0 at full saturation with freely available water to around 1000 kilopascals. This is measured in pascals, but kilopascals, because of the scale, is more adequate. Now, the water retention curve is basically the behavior of water content as a function of tension. So we have here a moisture retention curve. We will usually have the tension here in the x-axis in kilopascals, and this is also represented by the letter phi. And we have the volumetric water content here, either as a fraction or as a percent. I'm gonna write it here as a fraction between 0 and 1, which is equivalent to between 0 and 100%. What will normally happen is that you will start this curve at full saturation, so tension is 0, this is fully saturated with water, and this will be the maximum amount of water that the media can hold. So let's say we start here below 1 because the media takes up some volume. Initially, we will have some slight drop, so we will have a significant increase in tension with very little drop in volumetric water content. This happens many times. And this zone is usually the overwatered zone. So this is the zone where oxygen availability to roots is limited because we have too much water. Then we have a very steep decline of volumetric water content as a function of tension, where the tension changes very little and the volumetric water content changes a lot. And then we have this final zone, which is the final drying zone, which is the underwatered zone, let's say, which is where the plant, for a little bit of water uptake, needs to exert a lot of pressure. And then we arrive to a point here, which is around 300 kilopascals, where basically no uptake is possible. So after we reach this point, plants can no longer draw water from the media because the pressure needed is too much for most plant species, and therefore the media will draw water from the plant. So this is like critically underwater. This is where plants will usually wilt because the media will draw water out of the plant instead of the other way around. So basically we have here our no air zone, where there is very little air inside. Then we have this zone here, which is the high air zone, which is basically a zone where we have a lot of air availability and the plant needs to exert very little force to draw water from the media. And then we have the underwatered zone, and basically above these minus 300 kilopascals. Normally we put the negatives to the right here when we draw these curves, just for convenience. But basically above these minus 300 point, no water uptake is possible. Now, if you think about this, it is interesting to think about what the most ideal media and worst media in terms of moisture retention curves would look like. So we have our 0 to 1 here. We have volumetric water content, and we have our tension here in kilopascals. So how would the ideal medium look like? So you would start very close to 1 because the ideal media would allow you to have a lot of water. But then you would have almost no overwatering zone. So you would have a very small zone where tension increases a lot for very little drop of volumetric water content. Then you would have a very steep decline, almost vertical. And then you would have this zone here, and it would take a long time to reach minus 300. So what this means is that the media holds a lot of water. Then it is very easy for the plant to obtain that water, to almost fully dry the media. And then after it reaches this point, it takes a very, very long time for the plant to feel a lot of stress and eventually wilt. So it's a media that is ideal in every way. Now, what's the worst media? The worst media is something similar. It's the opposite of this. We have something that retains very little. So we have something that holds very little water. So basically, the media takes up most of the volume and water retention is very small. Then we have a very, very big overwatered zone. So the plant needs to exert a lot of pressure to draw even the tiniest bit of water. And then basically we can only draw water when we're close to this point where the plant cannot draw water anymore. So this is the worst. This is the worst. And this is the best. And this worst medium is usually something like growing in this. You can imagine this is like growing in a block of clay. So this is something that holds very little water because most of the volume is actually the media. So it's like a brick. It's a lump of clay. And then to even draw a little bit of the water, you need a ton of pressure because the media just holds onto that water like crazy. This best media here resembles something that holds to water very little and that holds a lot of water for the volume it has. So it's more like a Rockwool block. And this is something that we will see now with actual examples. So I wanted to show you these curves from Fonteno in 1996. In a 1996 paper, and I'll give you links to all these resources in the description. And what we have here are the moisture release curves, also the moisture retention, moisture release curves. These are the names that are given to these curves. So these are just moisture retention curves. And what we basically have here are different media that are being compared. So let's consider what we just discussed in terms of the best and the worst and different media and how they look like. So let's look at Rockwool here. So Rockwool here, and you can see it basically here. It's this square. So you have Rockwool here, and you can see how when we reach, we start very high. So we start here almost close to 100%. And then we are able to draw almost all this before we reach even 10 kilopascals. And this is the reason why a tensiometer for Rockwool is going to be very different from a tensiometer for soil. For soil, let's say we're talking about something like our normal soil mix that is a little bit clay heavy. You will probably water when you are at like -60 or something like that, like 60 kilopascals. In Rockwool, you will never reach that. The media will be completely dry before you reach that. You would reach that only for like the tiniest of time periods. You wouldn't be able to measure it. So in Rockwool, you want to water probably when you're at something like 7 kilopascals. And if you're watering at 7, then you need a tensiometer that is extremely sensitive. So this is why for Rockwool, we have special tensiometers, and even then, measuring these differences is very, very difficult. So this is why tensiometers are not the greatest choice when measuring to water Rockwool, because tension, when we get to -5, -7, the media will be almost dry. And if we want to preserve the volumetric water content of the Rockwool above 20% to prevent the media from becoming more hydrophobic, then we basically have a very, very little amount in terms of the tension range that we have to act. So tensiometers, this is why tensiometers are not very popular in Rockwool. They can be used, but then they need to be very, very sensitive. And you can see that the range is very, very small. But you can see here that the plant fights the media in no way. We have no overwatered zone, and this is basically, this starts going down very fast, and there is very, very little increase in tension for drawing almost all the water out of the Rockwool. Now let's compare that with core. We have here a coco core, and which is this one here. So let's look at for an equivalent dryback. So for an equivalent increase in tension, so for an equivalent increase in the effort that the plant has to do to draw water, the Rockwool has basically dried almost entirely, and the coco has only dried around 40% of the water content that it has. So you can see how the plant now needs to make a huge effort to dry this any further. And this goes out even more, and this becomes flatter and flatter as you go out. So you can see how coco is very different from Rockwool. Very, very different. And you can see perlite here is sort of an intermediate. So in the case of perlite, we start way lower. So we start at lower water retention because perlite cannot hold onto that water very efficiently. It takes a lot, the perlite itself takes a lot of volume, and the perlite is not able to retain that water as effectively as the core or the Rockwool. And then the tension increase that we have is similar. So to draw 40%, as you can see here, we go from 60 to 20, and we are at basically equivalent tension to what we would be in coco for something equivalent. So it behaves more closely to the coco than it does to the Rockwool. However, in practice, what you'll see is that you'll need to water more frequently, because here we are at way lower volumetric water content compared here to the coco. So although we would be at equivalent tension, this will dry back way more. We are at lower absolute water content relative to the coco. Now we have other interesting media here. For example, we have polystyrene, which is here, which starts very low, and basically we can dry it with almost no effort, but it retains very little. And this is very problematic because then we need to water super frequently. There is almost no tension increase as we dry all of this, but we need to water all the time because there is almost no water available for the plant. So when a media starts here very low, even if there's hardly any increase in tension, there is hardly any water. So this means the lower you start, the more frequently you'll need to water. So the ones that you would need to water the least here would be things like coco and Rockwool, and then perlite you would need to water a lot more, but then polystyrene you would need to water almost all the time. And then we have sand here. So sand, for example, here holds, the sand here is pretty coarse as well. Sand changes a lot depending on how coarse or fine the sand is. This is a pretty coarse sand. And you can see that we hold very little because the sand takes up a ton of the volume. If you have a block of sand, it will be mostly sand. So we can put very little water in it. And then we have a quite long overwatering zone here, well, compared to something like Rockwool. It isn't long by like traditional standards, but it is a significant overwatering period compared to Rockwool. And then we have this drop here that has relatively no big increase in tension. So this would be an acceptable media, but we would need to water it significantly more frequently, and we would need to be careful with this overwatering portion here. So while perlite and polystyrene, for example, we can hardly overwater, this one here we can overwater. Now, it would be tempting to think that you cannot overwater Rockwool, but you actually can overwater Rockwool. If you try to keep it always at 90%, you can see here that there is very little space for air. So the problem when you have very high starting water retention is that since you have very little air, you will overwater due to lack of oxygen, because if you do not allow this to drop, no oxygen can come in, and this will make the plant suffocate if you just dump water on it, because the dissolved oxygen is used by the plant very quickly. And for a large plant, the small amount of oxygen that is allowed by this gap is not gonna be enough, because there's media there, right? So the volume of air in there is very small. So the perlite you are way less likely to overwater because a more significant percentage of this volume here is air in addition to media. And then the polystyrene, you would almost never be able to overwater because it would just drain super quickly. You wouldn't retain the slightest bit. You retain very little. Now, let's look at another. So this is another similar graph that shows you different media comparisons, and we can see here again perlite and core, and we can see here something similar to what we just saw. So we have core starts way higher, perlite starts way lower, and perlite drops rather linearly in the beginning, but you can see that we end up we begin at way lower water content, so we will need to water these more frequently. These here are shredded pine wood, and these are pine wood chips. So this is shredded and this is chips. And when you are trying to test new media, this is very useful to figure out if they behave similar to anything else, and if they are close to the best or to the worst media graphs that I showed you before. You can see here peat, for example, as well. Behaves similar to coco, starts here, and overall has a similar graph. Okay, now I'm going to talk about this paper that I think is interesting because it is exactly what I just mentioned about you testing new media using water retention curves. So basically what they did was that they prepared rice hulls. They took rice hulls and they grounded up the rice hulls in different ways in order to obtain media, different types of media. So basically they ground the rice hull and then they put it through different screen sizes so that they would end up with media with different particle sizes. And then they tried to compare these to peat, or they didn't try, they compared it to peat. So we have the curve of peat here, and you can see that all these grounded rice hulls start up pretty high. So they have quite good water retention. And then the rice hulls, you can see these ones are gonna be the biggest particles, and these ones are going to be the smallest, I believe. Oh no, the other way around, sorry. These are gonna be the smallest and these are gonna be the biggest. So the smallest ones have these higher tension increases for the same loss in water content, because media that has smaller particle sizes will have bigger interactions with water. And you'll notice that if you go into like, for example, finer sands or finer particle sizes of any media, the finer, the greater the increase in tension, because the interactions between the media and the water will be greater. So if you compare any media with different particle sizes, you'll notice that the media that has the smallest particle sizes will usually have the largest increases in tension as a function of water content. So in this case, you would think that maybe these largest rice hulls have like the most ideal curves according to what we saw before. And this is true regarding water retention curves, but remember, water retention is not the only thing that we are concerned about. Another potential issue that we are concerned about is how homogeneous the watering is, which is something that the water retention curves do not show you. Because when you have media that has large particle sizes and you water it, it's easy for the water to channel through those particles. While if you have media with way smaller particle sizes, when you water it, the water has to find a path, and in finding that path, it will likely leak through the media if the media has a significant water affinity. So when you have media that has larger particle sizes, it might be more ideal in terms of the water retention curves, but you also need to consider how easy it is to homogeneously water the media, which is an important point. In this case, for example, the media with the smallest particle sizes might be slightly worse in its tension behavior, but it might be way better to water. So the moisture retention curves are a very important tool in order to evaluate the qualities of the media, and especially to evaluate if it is easy to overwater or underwater with a given media. But it is not the only characteristic of media that needs to be considered when deciding to use or not use a given set of media. So, through this video, I hope you learned a lot about moisture retention curves, and I hope you learned a lot about what is the ideal, what is the worst, how a moisture retention curve should look like, and how you can start evaluating whether a media is good or not according to its moisture retention curves. So, thank you very much for watching. Please remember to like and subscribe. I'll see you on the next one, and bye-bye.